Professor Richard Sowers. He's a professor in the Department of Mathematics and Industrial and Enterprise Systems Engineering at the University of Illinois at Urbana-Champaign. He has degrees in applied mathematics and electrical engineering, and his interest is in understanding complex urban data. And there is plenty of complex urban data here in New York. Go ahead, Professor Sowers. Thank you.
Thank you. So I'd like to thank the organizers for inviting me to speak. I started working on some interesting questions in urban traffic data a number of years ago, and the work I'm going to talk about was published and came out and appeared, and then I reconnected after several years with the Vision Zero rules of the road folks in New York City. So they asked me if I wanted to speak, and here we are. So this is sort of what we all know. Transportation is undergoing a generational disruption. When I was young, Uber didn't exist. Let's see, and everything else didn't exist that we see these days. So sort of a background question is, how do we actually sort of figure out what's going on in cities, and how do we use that to make decisions? Okay. So I'm going to be speaking about something called time for crashes, and I guess you all can, it's a paper there with this DOI. Okay, all right. So starting point was sort of my graduate students and I, we sort of started to look at several things. We started to look at traffic speeds, and we started to look at collisions, and we got data from these sources. And sort of the question is, how do we fuse data? How do we come out with a simple sort of way to think about crashes and traffic and everything that's going on in a city? And we wanted to do so in a way that would give some sort of simple way to compare things. So this is sort of a very simple story that I want to talk about. And it has some rearrangement of the data, but I think that it comes out with something that is useful at the end. And one of the exciting things about speaking at this conference is that I'm hoping that some of you will help me understand how to actually use this, how this might actually have an impact. So, okay, so let's actually talk about what we could get from this data set here. So estimates of traffic speeds and counts. Let me spend just a moment thinking about traffic speeds and counts. So there's a classic data set from taxis in New York City, and it was origin destination data, and it was scarily precise in origins and destinations. And we sort of took that as a starting point, or rather some folks that we borrowed the data from did. And they did some clever mathematics on it. They took the origin destination data, and for example, the data might say that it took 22 minutes to get from the green dot to the yellow dot, an origin destination pair. And then they said, let's just randomly select traffic speeds in all of New York City. And let's assume that taxi drivers are very efficient and find the shortest path between origin and destination. Maybe they were using Google Maps, maybe not, whatever, but then they would route themselves from green to yellow in the shortest way. And if by routing it didn't match up with the data or with our guess of speeds, then our guess of speeds were wrong. So we actually, well, in this paper or in this work, they actually reverse engineered speeds on many roads on New York City. Okay, so we actually started out in our data set with how fast traffic is moving on just about every road in New York City. Okay, so we had good data there. And we also had data from where crashes were actually occurring. So how can we actually combine this? Okay, so here's sort of the data, and it's I had to put four pictures together, so they're awfully squished. But we have crashes, we have is the left, we have trip origins, we have trip destinations, and then we have the actual pace, which is the reciprocal of speed. That means that high pace is slow speed. So reds are slow speeds. Okay, so we wanted to look at how all these things interact. Okay, where people are going. where accidents occurring, and how fast traffic is moving, and sort of all these things should interact, right? So somehow, if people are moving faster, maybe there's more likelihood of a crash. If more people are on the road, maybe there's more likelihood of a crash. So somehow all of these things fit together, and we were interested in actually taking this data and coming up with some sort of almost direct analysis from this data. We're not interested in building a real model. We're interested in directly looking at data and giving some sort of tool for comparison. Okay, all right. So this is sort of the story. Why are we interested in this? We're interested in coming up with some sort of succinct and, let's say, low-dimensional way to understand the interaction between traffic crashes, between where people are going and how quickly traffic is moving. And we want to do so in a way that would actually allow us to compare things, okay? Maybe compare before or after some sort of change in policy. We also want to compare different cities, okay? So what we're envisioning, or what we like, is some sort of tool which would allow city planners from New York City to take their analysis and compare the analysis to, let's say, Chicago or San Francisco, where we have a totally different street structure, totally different map, totally different numbers of people and everything. So we're interested in that sort of tool. One of the shortcomings of our analysis is that it is a static data analysis. It is what is the case. We're not interested, or we can't yet do, feedback, okay? So I'll talk a little bit about at the end, but this is somewhat limited. It's a data analysis picture. It doesn't tell us what to do or what would actually occur if we would change things, okay? So we started with OpenStreetMap model of Manhattan, lots of nodes, lots of links, and our data was in that interval 2012 from January to December. And there's lots and lots of data. So we had hourly traffic estimates. We did some sampling so that our computers would not complain too much. And we then used collision data from New York City, and that was the other thing. Okay, all right. So, and by the way, some of this actually, I think, reflects back or connects back to what Rob Viola was saying. He was interested in some interaction between geographics and demographics and interactions in crashes. So we're actually trying to build a tool which will inherently sort of connect demographics, well, traffic, let's say, or crash statistics, and also geography. All right, so trip count by hour, just to get a handle on the data. Not so many trips in the morning. We see a spike in the evening, see a spike in the morning. This is midday, then it tapers off and repeats. Okay, all right, so let's define some mathematical objects here, and then we'll organize them, okay? So let's consider just a path through the city. So we're going to follow a person driving along a path, okay? And the path goes from an origin to a destination, let's say, but we're going to count the historical number of crashes per hour along a path, okay? And I guess one background thought here is that I might not want my 90-year-old mother or my 17-year-old child to be driving through areas where there are likely to be a lot of crashes and, you know, things like that. So we're interested in sort of a trade-off between several things, time and crashes along a path. Okay, so let's consider the crashes per hour along a path. You know, we just sort of take the data. There's 20 crashes in this hour, in any given, you know, in between 9 and 10 in the morning per hour along a given path. And we're also going to consider the trip length, longer path. We're also going to consider how long it takes to get from A to B. We're all in a hurry. So what we're interested in here is a cost which allows us to sort of tune, to think about what a driver might be thinking about in trading between time and collisions. Okay, this is a thought experiment, but it'll actually give us some interesting results, I think. Okay, so we're going to have a crash aversion parameter alpha. And basically, if alpha is 0, we're going to think about the time it takes along the path. If alpha is equal to 1, where our cost is only going to be the crashes along the path. Okay, and then the question is, for a given origin and destination, what is the minimum cost path to get from O to B, from O to D? Okay, so what is the minimum cost way to get from your origin to your destination? Now, if our risk aversion, our crash aversion parameter alpha is 0, that means we're trying to take the fastest path. Okay. If our crash aversion parameter is 1, that means we are trying to take the safest path. Okay, so for each I only have 4 minutes. Yes, okay, for each origin and destination, what's the cheapest way to get from A to B? And this is sort of a picture for different risk aversion or crash aversion parameters. We have different paths, and let's then normalize by the fastest path. Okay, let's compare a different path to what you get from the fastest path. And looking at the time that I have available, let's actually speed along here. And we get the following interesting picture. Okay, if I'm willing to give up 15% of my trip time, I can decrease accidents by about from 1 to 8.825, which is about 17%. Okay, now this is sort of a sample data set, but here we get something more interesting. If I'm willing to give up 2% of my trip time, then I can decrease crashes by maybe 7%. That's if we're traveling in the morning. If we're traveling in the evening, if I'm willing to give up 1.5% of my time, I can actually decrease accidents by about 7 point something or other percent, and I can decrease crashes by less if I'm traveling at any other time in the day. So all of these are normalized, and I've also normalized by the entire number of trips in our data set. So if no one's traveling along the road, it won't count much. So we have these different plots here, and you can actually see sort of a difference between Upper Manhattan and Manhattan during the midday. And let's see what else I have here. Yeah. So the end result is several plots here. Manhattan morning rush hour, Manhattan midday, Upper Manhattan. So we can compare different regions, different times, all in the same plot. And I think I'm probably close to being out of time. So thank you for your time.
Thank you.
Am I out of time? So I guess I can field 1 or 2 questions.
You know what? I'm going to go ahead and save questions for all the speakers at the end, and we can get started. If Jennifer, if you want to start loading in to share your screen, we'll move on to Jennifer Norton.
And I will stop sharing after saying that the hard work was actually done by this young gentleman who's now at the Sensible City Lab at MIT.
Great. Thank you very much. Our next speaker is